Thank you for joining us on this Year 2 Energetics topic, Part 3, and we'll be looking at theoretical versus experimental lattice enthalpies and polarisability to help us explain the differences between different lattice enthalpies. So first of all, we're going to look at the definitions for theoretical and experimental lattice enthalpies and see if we can deduce the main difference between them. So if we start with theoretical, theoretical is based on a computer model. So it means just inputting certain data within a computer model and it churning out an enthalpic value, so a lattice enthalpy. Now that the way we input values, we input things like charge and ionic radii. Okay, and we'll also, when we input these values, we'll treat them as point charges. So ions are point charges. So what I mean by that is I'll have 2 points. One's a positive, one's a negative. I can account for whether it's a multiple charge on each of these ions, and I also can account for the distance between these two ions. So essentially what a theoretical lattice enthalpy deduces, it deduces purely the electrostatic attraction between these two ions. Okay, so we look at it in terms of 100% ionic. It's purely based on the strong electrostatic attraction between these oppositely charged ions. So 100% ionic bonding, and we'll put that there. Whereas if we look at experimental lattice, slightly differs. We've already calculated experimental lattice enthalpies using born-haber cycles. So using those born-haber cycles we've seen in previous videos, we can use born-haber cycles to calculate those experimental lattice enthalpies. The reason it's experimental is because the enthalpies you use in born-haber cycles are based off experimental data. So all those enthalpies that you might use within a born-haber cycle, someone has gone away and calculated those for you, not in a computer model. So these we look at these ions as not point charges. So ions are not point charges, but we still account for ionic radii and charge, multiple charges. So what it does account for is it accounts for polarization that occurs between these two ions, and therefore the covalent character. So this is what it accounts for. So that means we can do a couple of things. We can get a better understanding of the ionic model. We can also deduce the level of covalent character that occurs between different lattices, and we can also see the effect of that covalent character on the lattice enthalpy. So let's have a look at polarization and covalent character in a bit more detail. So in order to describe what polarization and polarisability are, I've drawn a few circles on the right hand side here. These are basically showing what ions are present. So I'm just going to keep it really simple and just say this is a positive ion and this is a negative ion. These two ions, you could tell pretty much they are the same size. Okay, now what I would say here is that this is 100% ionic, and the level of ionic bonding, or I should really say covalent bonding within an ionic bond or covalent character, is determined by the distortion of the negative ion. Now, distortion of the negative ion tends to occur when there is a highly charged positive ion and the size changes, and you can see that in this diagram underneath. So if I put this as a positive ion and this is my negative ion. Now, before we get into exactly what changes polarization, or the level of polarization, let's just have a look at what exactly is happening in this second diagram. Because of this ion being small and highly, well, it might be highly positive, might not, in this case it's just +1, we say it has a high charge density. So it's just, a charge density is a bit of terminology which describes the spread of charge over a particular volume. Now if that spread of charge over a volume is quite high, so in other words you might have a small volume, that increases the density, or if you might have a multiple charge which increases the density, the level of attraction on this negative cloud of electrons around the negative ion here, so this negative cloud becomes stronger, which means that this electron cloud starts to move over. It gets pulled over to the positive ion. This is called distortion. So I'll do that in black. Okay, this process is called distortion. That distortion leads to polarization. You can think of it in terms of a balloon, or even a ball, a football, or something inflated with air. If you squeeze the ball, you distort the shape of the ball. It is no longer spherical, and that's what's happening here. It is no longer spherical. It is now distorted going across. It's no longer round. And that leads to polarization, as I mentioned. So polarization always occurs due to the positive ion. And the level of polarization is determined by the ability for the positive ion, the cation, to distort the anion's electron density. Okay, so it's the ability for the cation to distort the electron cloud or electron density. Let's put electron cloud around the negative ion or anion. Okay. The polarizability, on the other hand, is in reference to the anion, the negative ion, is how easily is this negative ion distorted. Okay, so the polarizability refers to the ability for the anion, or the degree, it refers to the degree of which an anion is distorted. So the more distortion, the more polarizability of the negative ion or anion. A high polarization means the ability for that positive ion, the cation, it can cause a lot more distortion in the negative ion, the anion. Now that leads into covalent character. What I mean by that is, if there is more distortion, there is more covalent character. So if we make the first point, more distortion equals more covalent character. Now what do we mean by covalent character? Well, if we look back at this diagram here, we can see that actually this electron moving, these electrons moving over, this electron charge or density or cloud moving over, is making it look as if these electrons are starting to be shared between these two species. That means that it's starting to look like a covalent bond. It's not a covalent bond, it's still ionic, but it's giving characteristics or features of a covalent bond. So this is what we mean by it being covalent character. Whereas if we look at this one, there is no distortion of this anion, and therefore electrons are not being distorted and moving over, and there's no characteristical features of a covalent bond. Therefore it has no covalent character. Now the likelihood of an ionic bond being absolutely 100% ionic is very small, and there's always some degree or very little degree of covalent character. So covalent character is linked to distortion. Now this means that the distortion makes it appear as if the ionic bond is now looking like a covalent bond. Not very good English. It is not a covalent bond, it is still covalent character. Okay. So it's making it look like it's a covalent bond, but it's not. It's not 100% shared. It's just, it looks as if it's starting to be shared. So we say it's covalent character. So actually I've gone back and I've changed this definition a little bit. Well, actually quite a bit, to make it a bit more sense. So this means that the distortion makes it appear as if the electrons are starting to be shared. Makes it look like they're starting to be shared. This is what we mean by covalent character. It's not a covalent bond, it's just that covalent character. So this all impacts our lattice enthalpy. Now, because our theoretical lattice on the previous section, our theoretical is treating them as point charges, we are not looking at any distortion whatsoever in this negative ion. We just can't have any, which is why this is 100% ionic. Whereas our born-haber cycles for our experimental lattice enthalpy accounts for this polarization. Therefore we can determine or get an idea of how much covalent character there is there. So we're accounting for that electron cloud being in place. So we get this distortion, and we can also talk about, actually it's worth mentioning here, we can talk about this electron cloud or electron density filling this space between the two ions as it's being attracted by this positive ion. Now, in order to get a better idea of what kind of factors affect this level of distortion or the level of polarization, and therefore the amount of covalent character. Now, before we look at how polarization affects the enthalpies, lattice enthalpies, let's just have a look at how the radius and charge of an ion affects a lattice enthalpy. Now, I've got some data on the right hand side that I'll be using in a moment, but we're just going to focus on one of these columns. Don't worry that it says experimental or theoretical at the moment. We're not going to compare between them just yet. We just want to have a look at one data set. So let's just have a look at the first column to help us understand this. Now you can see on the left hand side I've drawn sodium chloride and potassium chloride. The key difference is that that the cation is different, so and they're both in the same group, so that means that sodium has a +1 and potassium has a +1, but the ionic radii increases as we go down the group, so potassium is larger, and that's because it has an additional electron shell or energy level in the group, and therefore you get that additional shielding, and hence as a result you're also going to get a larger ionic radii. But just looking at these two diagrams, the biggest effect we can see is that the distance between the center of this ion to this ion has increased as from sodium chloride to potassium chloride. So it's gotten bigger here because this ion, potassium ion, has gotten bigger. If we were looking at this as just point charges, the distance between the center of these 2 points, the nuclei essentially, would be increasing. Therefore, there is a reduction in the electrostatic attraction between the two ions. So what I've done is I've just put two red lines, and that shows the distance between the centre of the two ions. So we call this distance the inter-ionic radii, and the inter-ionic radii increases as that cation increases. So there's an increase in, just start that again, so there's an increase in, the inter-ionic radii. This in turn reduces the electrostatic attraction between the two ions. Okay, so that means that my lattice enthalpy, so I'm just going to put LE for short, the lattice enthalpy reduces. It becomes less negative, and it's always a good idea to describe it as less negative or more positive or less exothermic or more endothermic, rather than just saying low or high. So we can say that this means that lattice enthalpy becomes less exothermic, and it's the type of language you want to be using in your written answers in an exam. So less exothermic or less negative. So let's have a look at our data. That first column, we can see if we look at sodium chloride at the top here, and we look at potassium chloride here, we can see it has dropped, so it's become less negative from minus 780 to minus 711, not by much, but it has dropped. It's become less exothermic, and that is because of the difference between the size of ions, and that's because of that increase in inter-ionic radii. So just make that a bit clearer maybe. Inter-ionic radii has increased, therefore it reduces the electrostatic attraction between the two ions, and hence the lattice enthalpy becomes less exothermic. So that's radius. That's how radius affects the overall lattice enthalpy. Now we need to look at charge. So let's have a look at charge. Now what I've done is I've purposely picked two cations which are in the same period. So magnesium and sodium are in the same period. Now I've only got one magnesium compound here on the right hand side, but it's got iodide, so I want to pick sodium iodide for this one and compare it, and we can see straight away it's gone from minus 705, massive increase, to minus 2327. Kind of indicates that the charge has a bigger effect on the lattice enthalpy than the inter-ionic radii or the ionic radii of each ion. So this is quite important. So you can almost think of it as superseding anything. So we can make a couple of quick simple statements here, and we can say the higher the charge, the cation charge, the stronger the electrostatic attraction between the ions. Okay, so we can see that from the data on the right hand side. But how does the change in the negative ion, the anion, affect the lattice enthalpy? Now I've got two here at the top, sodium chloride and sodium iodide. Now chloride and iodide, or chlorine and iodine, are in the same group. We know iodine's a lot lower down than chlorine, so I know iodine is going to be a lot larger. And we can see the positive ion here hasn't changed, so that's static. The variable here that's changing is the negative ion, and we can see that the lattice enthalpy has become less negative, less exothermic. So the only thing that's changing is size, ionic size, not charge, just ionic size of the anion. So that must mean that this, what we've got here on the left hand side, holds true again. So if you increase the size of the anion, it will increase the interionic radii, it will reduce the electrostatic attraction between the two ions, and the lattice enthalpy becomes less exothermic. Now, something I forgot to maybe write down here, and it's just worth mentioning anyway, is the higher the cation charge, stronger the electrostatic attraction between the ions. So the LE, or the lattice enthalpy, becomes more exothermic, or more negative, which again the data supports. Okay. Right. Now we need to have a closer look at the differences between experimental and theoretical lattice enthalpies. So now that we've looked at how two particular variables or characteristics affect the lattice enthalpy by just looking at one of these data sets or one of these columns, let's have a look at how polarization actually affects the lattice enthalpy. And in order to do that, we need to look at the difference between theoretical and experimental lattice enthalpies. Now, what I've done pre-hand is I've written in the difference between these two values in red, and you can see that straight away the experimental lattice enthalpy is always more negative than the theoretical. Some of them are quite close, some of them are quite far apart. Now, you've got to remember that theoretical lattice enthalpies only treat the ions as point charges, so it accounts for no distortion whatsoever, whereas my experimental does, and that's what we're going to focus on. So what we need to do before we can explain those differences is to make sure we understand what kind of factors affect distortion. Now, again, I've pre-written this out, but these three rules, Fajan's rules, determine the level of distortion. Now, the way I've written these three rules, they actually tell us a way of suggesting that distortion is being increased. And let me put that a bit better. Each of these rules essentially tell us that there is more distortion. So if there's a high charge on the cation, if there is a small cation, or if it's a large anion, distortion increases. So all of this leads to an increase in distortion. Now, I've got a few diagrams underneath that I'm going to use to help explain this concept. Now, in order to do that, we're going to pair them up. So first of all, we're going to look at sodium chloride and sodium iodide. Now, the difference here is that the anions are different. The charges of the anion are exactly the same. It's just the size that we are looking at. Now, the size of the anion is more important than the actual charge of the anion. So, and the cation is staying the same, so it's the same size and the same charge. Now, because the anion has increased in size, this electron density is further away from the central nucleus, which means you can almost steal away this electron density a little bit more easily than you could the electron density here, because that's getting held in a bit more tighter from that nucleus. That nuclear attraction on those outer electrons is a bit more stronger, purely because iodine has got more shielding, more energy levels, and therefore the outer electrons are further away from the nucleus, less nuclear attraction, and therefore they can be distorted more easily. So if I was going to try and show this, I will definitely get some distortion of the chloride on here. Maybe not much, but I'll get some. Okay. But with the iodide ion, I'm going to get a lot more. Okay, so we can see this kind of oval egg shape forming. So I get a lot more distortion, and that's because of the large anion. So we're looking at rule number 3 here. Okay. More distortion means more covalent character. That is something worth remembering. So I've just written that here. So more distortion of the anion leads to more covalent character. And we can see that from this distortion of the iodide ion. And that again is because the iodide ion is a large anion. And the electrons, the electron density, is held less strongly by the nucleus. Okay, so additional shielding reduces nuclear attraction. Of the outer electrons, so they can be pulled away. So let's now pair them up again with another one. So I've already done sodium chloride. Let's look at potassium chloride as we did in the previous set of examples. Now what we can see quite obvious is that the cation is now changing, the anion is the same. So how does that affect the level of distortion? Now what we can see is that because potassium is in the same group, it's a larger cation, therefore it if it's lower down the group, it's more electron shells, more energy levels, more shielding. For the same reason, this is larger, because the outer electrons are held less tightly or less strongly, or there's less nuclear attraction on those outer electrons, so it's a bit more diffused. Therefore, we get a weaker attraction on these this electron cloud of the chloride. So we expect to see a little less distortion. What I'm actually going to do is I'm going to make the top one a little bit more obvious, more pronounced, so we have something to compare against. It's not very good. Okay, and we're gonna see that this is less distorted. Okay, we can see less distortion on this chloride ion because the potassium is larger and there's less attraction on this electron density. So this illustrates rule number 2. The smaller the cation, the more distortion. The sodium ion here is the small cation and it leads to more distortion, okay, than the potassium ion, although these almost look the same, but this is slightly more distortion or more polarization occurring here. Therefore, there is more covalent character in sodium chloride than there is potassium chloride. So there's less distortion and less covalent character. And that's purely because we've got a larger cation. But what happens if I increase the charge on the cation? So this is actually the first rule we're going to be looking at here. So this one here, a high charge cation. And what we're going to do is we're going to pair off sodium iodide and magnesium iodide, because sodium and magnesium are in the same period on the periodic table. So they have the same number of electrons, they are isoelectronic to each other, and also therefore those outer electrons on the cation will experience a different amount of pull only due to the nuclear charge of each ion. Now the idea is that the main key point is that it's now 2+, not +1, and actually, although it doesn't look here, magnesium should be smaller than sodium, so I might just change that now. Okay, so that's a little bit better. We can also see it's a bit smaller. So although we're only looking at charge here, some of this reasoning will be because of the size too. So let's move that a little bit in place. Okay, so as a result of that high charge cation, we are going to get more distortion, and that means that there is going to be a great deal of attraction. So this electron density is starting to fill in that space, the void between these two ions, almost making it look very covalent. And because of the level of distortion, a much higher level of distortion, so in fact I might just make this a little bit more. In some cases you can see diagrams where they almost show it encapsulating the magnesium, or the negative ion, the positive ion, sorry. So we can see a greater deal of distortion. So more distortion, more covalent character. So I'm just going to write more distortion here. And that's because of the highly charged, so high charged or highly charged cation. And yes, it is a bit smaller. Also smaller than sodium. Now this is quite important because actually magnesium illustrates two things. One, there is more distortion because of a higher charge, and actually there's more distortion because it's a smaller cation. And that all leads to a concept called charge density. Alright, so, and this is something we spoke about before. So charge density is the spread of charge across an ion. The more concentrated that spread of charge, so the less spread it is, the more polarization there will be, that will occur, and obviously the spread of charge, I'm talking about the higher the charge density on the cation, the more distortion there is. So if I look at magnesium, it's small and it's high charge. So the higher the charge density, on the cation, the more distortion and hence covalent character. And the charge density relates to two things. It relates to ionic size or ionic radii and charge. If the charge is high and the ionic radii is small, then it's a high charge density. And that's why we can see that there is more distortion with the magnesium ion and iodide than there is with the sodium and iodide ion. The charge density of the magnesium ion is a lot higher. So it's a much higher charge density. Okay, that says charge density. If I was going to compare the sodium to the potassium, sodium chloride, potassium chloride, this has a higher charge density than a potassium ion because it's smaller. Same charge but smaller, higher charge density. Now what we also need to look at here is what does this do to the experimental lattice enthalpy, and how can we suggest the level of covalent character in an ionic bond? Well, if we look back to our data and we compare our experimental to our theoretical lattice enthalpy, you remember that I worked out the difference between each of these lattice enthalpies. Okay, now the reason I did that is because it tells us or shows us the agreement between these two lattice enthalpies, how close that agreement is. Now if you look at sodium chloride, it's quite close, it's 10. So there's very little covalent character within the experimental lattice enthalpy, right? Because the difference between them is quite small. And we can say the same thing for potassium chloride. And if you remember from before, the potassium chloride, there's less distortion, even less covalent character than potassium chloride, which is why the difference between these two lattice enthalpies is very small, and it's not far off the difference with sodium chloride. Whereas if we start to look at sodium iodide, we can see that because of the large iodide ion, there is more distortion, even though it's still sodium. So we start to see bigger discrepancy or a bigger difference between the two. So we can say because the difference is larger and well, as a result the experimental lattice enthalpy is more exothermic or more negative, we can say there is more distortion or more covalent character, more specifically within this ionic lattice. If I jump to silver chloride, there is a much bigger difference there. So there is more distortion, it's showing more distortion in that lattice enthalpy, so more covalent character. And again with the magnesium iodide, which we looked at here, and you can see the amount of shaded grey there, there's lots of distortion and there's a huge amount of covalent character. Still ionic bond, but there's even more because that difference is so huge and it makes it more exothermic. So the other thing that we can take away from this is the more covalent character, the more negative the lattice enthalpy, and therefore it takes more energy to break the lattice. So that's really quite important. So really important point here. Covalent character leads to a more exothermic, let's write exo, lattice enthalpy. And therefore, to break that lattice, the lattice requires more energy. So the more negative or more exothermic the lattice enthalpy, the stronger the lattice is, and covalent character, any covalent character you have within an ionic bond actually leads to the enthalpy being more exothermic, which we can see. Let's just take this one again here. Okay, we can see it's more exothermic here, so the lattice structure is actually much stronger as a result of it. And these are typical exam questions where they ask you to explain the difference between theoretical and experimental. You need to talk about the experimental lattice enthalpy accounting for covalent character and distortion, which makes the lattice enthalpy more negative or more exothermic, so it requires more energy to break those or that lattice. So the lattice enthalpy or the lattice dissociation enthalpy is more endothermic. The other points that we need to look at is just if I say to you which one will have the most negative lattice enthalpy, sodium iodide or magnesium iodide. Well, first of all, you just say that iodide is the same in both molecules, or not molecules, both lattices, but the difference is the sodium and the magnesium. Magnesium is a much higher charge. It is therefore, and it's also smaller than the sodium because they are both in the same period. Magnesium's got a higher nuclear charge. Electrons are pulled in more closer, so it's smaller, higher charge, therefore a higher charge density as a result. So we want to talk about highly charged, also smaller, therefore high charge density, more distortion of the iodide ion, and therefore that leads to more covalent character and hence makes the lattice enthalpy more negative. So it has a more exothermic lattice enthalpy. Okay, so that's another thing that we can use to answer questions like I've mentioned. Now that takes us to the end of this video. I hope it was useful. If you did find it useful, hit the like button below. Also use the comment section to let us know of any other videos you might want to see, and if you want to subscribe, you can keep up to date with any other videos we upload. So hopefully we see you next time, and bye bye for now.